Unit 15, Part 12, we're continuing with Klenk 286, example J, done slightly differently to how she presents it there.
We're gonna draw outside.
Alright, bye kids.
Bye. Bye, Daddy. Bye.
So I filled out a bit more of the proof. Those are the premises again. That's the conclusion, right? So we saw that we needed this instance to get the conclusion. We set up a conditional proof. We did that a bit before. Klenk did hers. Okay, so I've filled out a bit more here, and I've left it here to point something out. Right, we followed the crucial advice of hard before easy, setting up for UG before doing universal instantiations. Right, that's why the flag subproof is on the outside. The flagging step becomes before the UIs. Okay, so C, hard before easy, set up for UG before you doing UI. See how it looks in practice. It's the fact that step 3 appears before steps here 5 and 6, or in Klenk's text it's 3 and 4. She does these before she sets up the conditional proof. That doesn't matter so much. Right, so we've got the UIs. That's what allowed us to instantiate. Because UI is an unrestricted rule, we are allowed to instantiate to A, to the letter, to the individual A, even though A has been flagged. Right, that's fine. That's exactly what we want. Right, we want to get, well, this is the step from which we're doing the UG. We want to derive the propositional true that's true of an individual, the propositional function that's true of the individual A in such a way that it would be true of any individual, right? Going back to Klenk's page 281, which I read several times, but repetition is good. The kind of instances from which it is proper to infer universal propositions are those that would hold as well for any other individual. In practice, and in this example, this usually means those that were derived entirely from universal propositions, which is what we've got here. Right? This instance is derived from universal propositions. Just 1 and 2 is going to get us there. All right, so we've got the universal instantiations, okay? And we do also have GA, noticed, right? We flagged A, but when we set up the conditional proof, we got a formula, we got GA. GA is almost the antecedent of this conditional we got from UI on 1, right? So we just add to GA. Look again at the formal rule for addition. You can add to the left or to the right. Right? The two forms are given P, you can infer P or Q, or given Q, you can infer P or Q. So the result of addition is always a disjunction. You can add the formula you're adding to the left or the right. So just pointing that out because here we're adding FA to the left, right? Why? Because that's what we want. GA or FA is not the antecedent of this, although if you did add, if you were used to the one form of the add and you added to get GA or FA, you could then turn that into FA or GA by the rule of COM, C-O-M-M, commutation. Okay, so we've got the antecedent, modus ponens, we derive the consequent, De Morgan's, or this should be very familiar, De Morgan's gets us that, and we simplify to get not HA. All right, I stopped at this point. Where are we going and how do we get there? Okay, what do we need? Right, notice that because we've done the right thing in doing the universal, when setting up the UG step, we put the instance down the bottom, so we know that we're going to that. We looked at where we were going and we saw that it's a conditional, so we set up for a conditional proof. We did that the right way, which is to say we not only assumed the antecedent, but we put the consequent down the bottom, which tells us where we're going. So we know we're aiming towards, and we're done when we get not said A. Okay, where's it going to come from? Well, look here. What we need is the negation of the antecedent of this conditional, right? What rule allows us to derive the negation of antecedents? Modus tollens, right? So I'm probably going to get this by modus tollens. What do I need? to get this by modus tollens? That is, I've derived this conditional. Modus tollens is a rule with two premises and a conclusion. We just figured out that this is the conclusion that I want. What's the other formula I need to satisfy the rule? What's the other formula I need such that I have got substitution instances of both premises of modus tollens, right? To you do modus tollens on a conditional, I need the negation of the consequent, right? Because what is the rule? What is modus tollens? It says, given a conditional and given the negation of the consequent, you're entitled to infer the negation of the antecedent, right? Have all those thoughts, and you're at the thought. You're at the thought that that's the formula you need, right? You need the negation of the consequent. Okay, how do I get there? Well, I notice that I've got not HA, right? I want you to notice that, right? What I need is the negation of a conjunction, right? This particular conjunction, but more generally, I need the negation of this conjunction, and I do actually already have, right at this step, I have the negation of one of the conjuncts, right? If you say that clearly enough, you should hit upon the thought, aha, I remember way back in Unit 8, these really cool things that my professor jumped up and down about and said were the coolest things ever, called proof bits. And these little proof bits were subroutines which allowed you to get from certain formulas to certain other formulas. For example, given the consequent of a conditional, I can derive any conditional. Right? There's an add trick that I can do, an addition trick. Right? Given the negation of the antecedent of any conditional, I can derive that conditional. And right, I can derive the negation of a conjunction given the negation of one of the disjuncts. I remember that there is a path from there to there, right? So if you were somehow stuck there, or if reading steps 10 through 12 of Klenk's, slightly different numbers from ours, but steps 10 through 12 of Klenk's page 286, and you're like, why did she do that? How did she? It's just the application of this proof bit, right? So that's why she does, right? So what is the actual proof bit, right? Thinking De Morgan's backwards, this is equivalent to what? Think of it this way, this is equivalent to not P or Q. Oh look, this is in the